expertise in the fields of reactor safety. So this is also the field in which I am working, mainly on the enhancement and or development and validation of our system code ATLET for the mainly for the simulation of cooling circuits in reactors. But we have also experts in physical protection, storage and final disposal of radioactive waste, radiation protection, environment and energy, and decommissioning and dismantling. So that's for the advertisement part. Let's go to the main topic, a general overview. You had already some presentations about SMR, and what you saw maybe is that especially for light water SMRs, the reactors are smaller and are more simplified than larger reactors. This, let's say, is mainly, I think, due to cost reduction. You see that large water reactors, when they are built today, are very costly and very expensive, and so there's the need of cost reduction, let's say. And then against that, you have the topic of the protection against ionizing radiation. You have the fundamental safety functions, reactivity control, cooling of the core, and the confinement of radioactive material. And taking both points together, let's say you see in the SMR designs a lot of inherent safety features, passive safety features, and other innovative features. Let's come to the inherent safety features. First point is the core. On the right side, you have some examples. The first one is the NuScale reactor, and the second one is the CAREM reactor. And here you see basically that the core is mainly in a very low position within the RPV and has a large water inventory above it. And so this extends, let's say, the time during LOCA until the core becomes dry. We have a reliable and effective heat removal by a reduced power density. So you can say you have 25% less power density compared with current PWRs. You have a smaller distance between core and RPV wall, which enhances heat removal. And you have a larger surface to volume ratio due to the thinner design, let's say. Some of the reactors also spare out a boron system, at least for normal operation. And so examples are the Nuward or the Rolls-Royce SMR. This eliminates, of course, the deboration accidents. But on the other hand, you need something in order to compensate your excess reactivity. And this is done mainly in these designs by the control rods, and burnable absorbers, which are, for example, included already in the fuel. And this can lead somehow to possible challenges for safety demonstration. So, for example, if the absorbers are depleted at the end of cycle, this can lead to reactivity peaks. You have the problem of the prediction of the depletion of heavy used control rods. These control rods deplete quite quickly if they are inserted deeply in the core. If the absorbers are integrated in the fuel, this also impacts the heat conductivity and the density of the fuel. And you have to consider this in your safety demonstration. And for rod ejection accidents, this might be also a problem if the rod worth is very high and effective. And when one rod is ejected, this is can be a large problem. Okay, and since these SMR should also be deployed in remote locations, and also due to cost reduction, we see a very long fuel cycle or fuel element cycle. So above 2 years, let's say, is quite normal, and this is reached. Okay, due to the burnable absorbers and sometimes also boron acid, but we have let's say two designs, mainly Russian designs, which is the Rhythm 200 and the what was it, the KLT 40S in the academic Lomonosov, which have a very high enrichment in order to achieve these long fuel element cycles and high burn-ups. And this can be somehow a proliferation issue, because the enrichment is nearly, let's say, nearly 20% in these designs. The cores are shorter normally. When you have a look at the correlations for critical heat flux, this can be an advantage, because normally in the correlations, an entry length is needed, and if the cores are shorter, then the critical heat flux might be less important. You have also smaller cores, leading to a higher leakage in this way. You need maybe a heavy reflector around the core, and this can affect also the validity of your computational tools, especially for your diffusion approximation in the neutron transport equations. And some of the in some of the designs, also advanced accident tolerant fuels are considered, leading to potential higher safety margins. But you need to know that this topic is currently subject of active and ongoing research, so it's not finished yet. And I think if one SMR would be built today, maybe ATF wouldn't play a large role. We have as another topic the so-called integral design. When you have a look at the left picture here, you see that in a large PWR, all of the different parts, like steam generators and pressurizer and piping and so on, is outside of the RPV. This is quite normal for the large LWRs, and in the SMR cases, normally all these primary parts are integrated inside the PWR, inside the RPV. As shown here in the example of the new scale, we have here on the right side here the steam generators. We have a pressurizer here on the top, and this is all integrated in this one vessel. This leads to some advantages. The absence of large coolant pipes limits the maximum possible LOCA size. So, for example, in a large PWR, you can say that the largest leak size is of about 1 square meter, and I think in the CAREM reactor, when you have a look at the largest break size, it's less than this. It's 0.0014 square meter. Additionally, the number of connecting pipes is minimized, which is also an advantage, because it lowers the possibility of a LOCA. The connection nozzles are normally above the core, so you have this, what I already mentioned, this large water column above the core during the LOCA. the RPVs are high and narrow, which is good for natural circulation. And in some designs, I think not in the new scale designs, but in other designs, the control rod drive mechanisms are also integrated inside the RPV, which eliminates the rod ejection accident I spoke earlier on, since the pressure differences are lower. So some words to passive safety features in general. So passive safety features are not new in the nuclear field, but they are heavily used in the SMR designs. So a passive safety system in general does not need any external power, and it is based on small driving forces like convection, evaporation, condensation, and gravity. And the classification whether a system is passive or whether it's not passive, this depends on the national regulatory practice. So, for example, in the IAEA definition, there are 4 categories for passive systems. Let's say you have a category A, for example. In this category, no moving fluids, no moving mechanical parts, and no signals are allowed. So just structures and let's say heat conduction. In category B, moving fluid is allowed, and this goes on until category D, in which also signals are allowed, for example, in order to activate maybe a passive system by opening a valve. And so all these systems would be passive, more or less, but in the German regulation, for example, category A and B would be only passive, and C and D would be an active system. And depending on this classification, you also have the points, for example, of the single failure criterion in your safety demonstration, for example. So in some regulations, you don't need to consider a single failure for passive safety systems. And so it's needed to know whether a system is passive or not. The most passive safety systems are based on natural circulation, I think. And I just want to show you maybe some things about that. On the right side, you have a scheme on a very simple circuit with one heater and a cooler, and they are connected by pipes. And you have different densities due to heating and cooling here in these pipes. And due to this density difference, you have a driving force, which is the driving force is due to the densities, let's say. You can calculate it. Due to constant heating and cooling, this flow would be steady. The only necessary thing is here that the heat source must be below the heat sink. And this can be enhanced a little bit if the heater here evaporates the fluid, since then the density is much lower. And the flow is then balanced by the pressure losses, mainly by friction losses on the pipes and so on, and also by form losses, which you have due to the bends here, flow path extensions and restrictions. You might have some valves, some blends and so on. And then you can calculate here maybe the flow velocity if you want to. In general, this is a very simple example. General in a real plant, this is much more difficult because, for example, maybe the friction and the form losses might also depend on the velocity and on the Reynolds number, and so this is not so easy as it's shown here, but it should give you an idea of it. So safety demonstration for passive safety systems can be challenging due to the very small driving forces, you have high uncertainties on them. Small changes in boundary conditions can influence the safety behavior. Some passive safety systems have a nonlinear characteristic and can lead to operating regimes depending also on overall plant feedbacks. The testing is difficult, so normally you should test it under plant conditions, but this can be difficult. If you have heat transfer, then non-condensable gases can affect it. When you want to do this safety demonstration by use of numerical tools or something like that, these evidence tools also have uncertainties, and they need also some high precision models which can lack in your simulation. And a very important thing, I think, is that too efficient operation of these systems can also be problematic. So if you think about subcooling transients, for example. So I have now some examples of different kind of, let's say, safety systems. The first is about the residual heat removal. In WP1, in our first work package in ELSMOR, we screened a large list of different SMR designs and had a look what kind of systems they are using and collected them a little bit together. And this is a result of this investigation, let's say. So the first possibility how to do this residual heat removal is the cooling by the secondary site. So normally this can be actively. This is maybe the normal way, but if your active systems and your condenser are not working, then you have some other possibilities. For example, you do this passively by a water pool, as shown here on the right side. You just condense the steam in this heat exchanger here, and the condensate is flowing back. This can also be done by an airflow. So, and an example of that is here the NuScale reactor. So in an accident case, you would close here the isolation valves for the feed water and for the main steam line also, and the steam from the heat exchanger would flow through these heat exchangers here, which are located in the pool. And the steam would condense and flow back to the to the steam generator, and and would evaporate again. So this would be an example for this kind of system. And during this operation, after I don't know, I think after 30 days or so, this pool is expected to get dry because all of the water is evaporated. And then in this design, it is foreseen that that it should be possible to cool the reactor only by an airflow and an air cooling of this decay heat removal heat exchanger here. So, okay, actively by made heat sink can be found in all designs. You can also cool the primary site directly just by taking the steam or water from the primary site and cooling it inside water pools, like in these designs. It's also possible to do it by an extra circuit, an intermediate circuit, in which you take the heat here in this heat exchanger, providing steam in this intermediate circuit and condensing it again in this water pool. This is done, for example, in the NuVart design, as shown here. This is the RPV, the heated primary fluid flows here into these heat exchangers, heating up the intermediate fluid here, which is evaporating and then finally condensing inside this heat exchanger here. And this heat exchanger is then again connected to the large water tank in which the whole containment is located. So this is an example for that. Okay, and then you have other active systems, which I won't show here. For emergency core cooling, active systems are commonly found here in this designs. And passive systems you find also. Accumulators are not new in the nuclear field. You find it also in large PWR. But they are shown here on the right side. Basically, it's a large tank which is pressurized by gas, mainly nitrogen, for example, and you have water here, and at some pressure in the primary circuit, you open here the isolation valve, or maybe it's also possible that it opens by itself, and then the water is injected into the cooling circuit. So this is mainly for lower pressures. For higher pressures, you find makeup tanks, so-called makeup tanks, which are also common in larger PWR designs. Here, the idea is that you have a circuit, let's say, and a large tank in it. You have to open the isolation valves, and then by natural circulation, the water inside this tank is injected into the cooling circuit. In some designs, there's also an additional heat exchanger here in this makeup tank, and then you have really a natural circulation, because you have here the cooling, and somewhere below there is the core, and there's the heating, and then you have natural circulation. Okay, elevated tanks work quite similar, but here the pressure is provided by the high elevation, so by the hydrostatic pressure, let's say. And then finally you have long-term cooling from a sump and a pit. So in large PWRs, you have normally also a sump, and then you have for low pressure injection, taking the water from the sump and injecting it to the primary system. And in some designs of the SMR, this is done passively by a small valve inside the RPV wall. And okay, when you have a leak, you have somehow a steam condensation here, and the water is collected in the sump. And when the water column is high enough, so that the pressure here is higher than in the RPV, then you have a backflow of water into the RPV. This is done also in the NuScale, for example. You have this recirculation valves. And okay, in this example, there's no leak, but you have vent valves, and these vent valves are venting the steam into the containment. Here it's condensed, collected in this lower part. And yeah, as I already said before, if the column here is heavier than the column here, then you have a recirculation. Primary depressurization. This is also needed in order to control the primary pressure. This can be done, for example, by a relief valve on the pressurizer section of the RPV, and you have a steam flow then, for example, into a water tank, and then it's condensed there. Maybe also additionally with a backflow of condensate later on. You have the depressurization into the containment. For example, it's the same picture as before in the NuScale case here. And okay, then you have some purification and cool down systems in other reactors. I think this is the final part here, containment pressure control. There are also different possibilities found in the literature of the designs. First of all, there are containment condensers. These containment condensers work in such a way that you have normally a pool above inside the containment, and you have the pool above the containment, let's say, and inside the containment there's a condenser which is connected to the pool, and steam coming by a leak or something like that can condense here on the condenser, and this controls the pressure here. Another possibility is a blowdown into an external pool, or you have a wet well, which then you need also a dry well. And this is some kind of a strategy like in the BWR. This containment condenser is also not a new invention. You can find it also in other reactor designs, like in the Kirena, for example. There you have this condenser, and in some Russian designs you have also these condensers. And but they are also used in the SMR cases. So then there are other possibilities, for example, a spray into the containment atmosphere. So you spray just water droplets into the containment, and steam can condense then on these water droplets. And finally, there's a condensation on the containment inner wall, as in the NuScale case, for example, but also, let's say, in the NuWard cases, also this possibility provided. And the idea is just to condense the steam here on the wall and transfer the heat into the outer water pool, taking the heat, and possibility is that you wait until you can transfer the heat to the air, or if this is not possible, you need to refill somehow the pool. For safety demonstration with respect to the containment pressure control, there are also some challenges. So here in the containment, you have a large amount of non-condensable gases, mainly air, or if it's inerted, then you have maybe nitrogen, and this impacts the condensation heat transfer, for example, on the inner wall. You have the natural convection on high containment walls when inside a water pool. Here, maybe for this statement, it is needed to know that correlations for the heat transfer of natural circulation are only valid for quite low heights, let's say for 1 meter plates or something like that. And but these high containment walls have a height of, let's say, 20 meters or something, and especially in our department, in the development of our system codes, we had this problem that, okay, we need some more data and more correlations also for these higher walls. We have the fact of the small containments. There you have the problem that although the LOCA size is quite limited, as I said before, due to the integral designs, you have a high pressure during the LOCA because the containment is quite small, and therefore high loads on the containment wall. So you have although you have this limited sizes, you need to have a look at that. In the NuScale containment example, for example, there is a very high design pressure. So this is the solution here, and then you need somehow these systems I showed you before in order to control the pressure by spraying by the pool and other kinds of systems. So let's come to defense against external hazards. There are mainly 3 different approaches against external hazards, like earthquakes, explosions, airplane crashes, and flooding. The first one is that the modules are located inside large water pools and inside caverns below the ground, as shown here in the mPower case. The modules are located below the ground. Here, the water pool is only on the top of this containment vessel structure here. And in the NuScale case, this is also here the point that you have this water pool and it's below the ground. So this is one point. One other point is that you have floating SMR. Depending on its location, so when it's maybe 100 kilometers away from the
Sure.
Sorry, from the shore. Yeah, okay, from the shore. Thank you. Then you might have no impact of tsunamis, let's say, or earthquakes. So depending on the location, this is true. The ocean works as an unlimited heat source. You can use this. But for safety demonstration, for example, you need to consider transport hazards. And the sea motion is very important. The whole barge can move due to the motion, and you need to have a look at the impact of the Coriolis forces, and this must be investigated. And if you use then additionally passive safety systems, which are based on gravity, this can be quite challenging, let's say. Okay, and the last one is SMR on the ocean floor. Here, normally, the control rooms are onshore. The ocean, as I already said, works as an unlimited heat source, and yeah, you need a remote operation because yeah, nobody can stay at the modules below the or on the ocean floor very long, let's say. Okay, some last words about severe accidents, maybe. There's the point of practical elimination. So during the design and also for safety demonstration, you need to practically eliminate sequences, events, or situations which can lead to early and or large releases. And this can be demonstrated normally by either that the sequence is physically impossible by the design, or by the demonstration that the sequence is highly unlikely with a high degree of confidence. But although you show that some sequences are practically eliminated, which could lead to this severe accidents, they are still needed to be investigated, and you need to have some severe accident management. And here the thing is that you should do some first development of such severe accident management already during the design of the reactor. And for the melt retention, we saw that the in-vessel melt retention with external cooling is preferred against the ex-vessel melt retention in the most designs. We see there are 2 points. Let's say the first one is that it's quite difficult to integrate a core catcher into a very compact containment. So this can be a problem. And yeah, ex-vessel cooling with recirculation of the vessel is already a safety feature in some designs. So you already have this possibility, and then you can use it for your in-vessel melt retention. So this is last slide, I think. I'm good in time. Some conclusions. We have a large number. We saw this during the WP1 work. And this large number of designs have a large number also of different safety features, and we saw that basically that the simplification is needed in order to reduce costs and increase the safety. We have a size reduction. We have the integration of the components into the RPV, and we have the use of passive safety systems. But all of this is quite new and more or less, and this innovative components and passive systems can challenge the safety demonstration. So this is quite important, let's say, if you want to deploy your SMR somewhere. So that's all. I have here also some references for mainly for the pictures I used. And so this is all from my side. Thank you very much for your attention. And I would, if you have any questions, just ask.
Let me start with a question from the floor, from the people that are online. Ahmed is asking, borated water is allowed to be injected for the emergency cases? Because you mentioned the solution from Newark and other SMRs that they are not using boron diluted in the primary fluid. So if this is the case, are they anyway thinking about injecting boron for safety features?
Yeah, normally in most, I think in all regulations, you need a redundant and diversified system also to shut down the core, and for security reasons, and for you need a second system in order to shut down the core, and this is normally a boron system, but you don't use it in some designs for the normal operation, let's say, so like in the BWR maybe.
Okay, thank you. Vil, one question from
it's a
comment from
you. Comment there. Some designs do try not to use the boron as a secondary system, but I don't think that it has yet passed in any licensing discussion. So there is basically attempt at not have any boron, but who knows whether it will pass.
Okay. So we will ask tomorrow to Sean about what the safety authority may think about having a boron-free core. Other question from the floor, please.
There was a reactor on SMR on ocean floor, the Flex Blue. How deep can the reactors be situated in the ocean?
Sebastian, what about Flex Blue and other solutions? Because I remember MIT is proposing to have not submerged, but almost submerged anyway on a floating structure like the oil rigs in the middle of the ocean. But specifically, the question is about Flex Blue. How deep into the sea?
I'm not sure about this anymore. I think it's quite near the shore, but it's not that away like in the MIT in the MIT design. I think maybe 10 to 20 meters below the water, I would say, but I'm not so sure about that anymore. But yeah, and I don't think that that Flex Blue will be built in the near future. And in this MIT, I think you already said it. I think all of the containment should be below the water, and it's just hanging from the platform somehow.
Yes, even myself, I'm not sure, but if I well remember, Flex Blue, they claim that they may put the hull on the sea floor, on the seabed, from 30 meters to 100 meters.
Okay, then it's
over the sea level, so it's not so deep. But anyway, more than enough to have the seawater cooling for an indefinite time. The hull, hence the reactor core. Other questions? One question from.
Thank you for the presentation. I would like to ask, we spoke about, speaking about the floating SMR and the ocean floor SMR. We spoke that, in particular for the ocean floor, we spoke about an onshore control room. So we need a sort of remote control. We spoke about eliminating all the dangers like earthquakes, tsunamis, but what about the informatic cyber attacks? This may be a problem.
cyber attack. Yeah, this is a problem, and especially, let's say, if you have this common control room, then all of these reactors would be affected by this attack, and I think you need some more security against this. Yeah, but to be honest, I'm not an expert in the cyber security, let's say.
You are not an hacker, Sebastian. So,
You're right. Yeah.
Anyway, I think that this type of issue is really not only limited to SMR. So I think that this is a new environment that is affecting all the nuclear reactors, probably especially the oldest one, I would say. Even if the problem of cyber attacks is usually mainly addressed by the designer by avoiding that critical systems for safety and for main control are connected to the web, to the external. I don't know if I will remember, Sean. I don't know if you are an expert also on that.
I actually know a little bit about that. So for cybersecurity, from a regulator point of view, from a safety point of view, to sort of recognize that you can't be on top of every different cyber attack or every different technique that they have. What we regulate is you have a program in place to be continuously updated so that your cybersecurity can evolve as threats and as threats evolve. That's sort of one purpose. The other thing too that we always consider from a licensing point of view is what happens if that cyber defense fails. So what are the consequences of that failure if you do have a cyber attack that's successful? You mentioned for our existing plants, a lot of those systems are very old. We hope they focus more on isolation of those systems and ensuring that they can't get access from the internet or other means. For some of the newer systems, they used to have levels of defense in depth. So one of them is the internet. There's an internal system that you'll use, and then there's components that stay by themselves. So we don't regulate specific things for cybersecurity, but we do expect there's a program in place. It's constantly evolving to meet the challenges of new threats, which are changed almost every day.
Thank you. Thank you very much. Other questions for Sebastian? No. So let me give you one last question for you, Sebastian. What is the lesson learned from this activity, in your opinion? So you addressed the work package that you are leading. Addressed really a lot of SMR design. You look into several safety systems, several features related to safety. If you have to synthesize in a few words, what is the main lesson learned from this activity? What would you suggest? What is the takeaway for us for this anyway very important issue that is safety?
Let's say the point is that you have a very large number of these SMR designs, and you have a large number of different approaches how to cope with the accidents. Some points are quite similar, but in the details they are quite different. And when you have a look at this and you see you need to have your safety demonstration somehow, then you see that you have, this is a point later on, a large number of challenges in your safety demonstration you need to think about, and just due to the fact that you have this simplified designs, and this makes the safety demonstration quite difficult, let's say. And especially then when you want to deploy these SMR into different countries in which the regulations are also different, and then there come one point to the other, and this is quite challenging, let's say.
Thank you, and this is why tomorrow we will have the seminar from Sean on this specific topic. So thank you once more, Sebastian, for coming and for offering us your speech, your seminar, and I hope to see you soon live. And again, thank you once more. Thank you.
Yeah, thank you very much, and have a good time during the week.
Thank you. I think that now is time for the lunch, right? Okay. Okay. Can we leave all the stuff here and we lock the door? Okay. Or we stay here to check? Okay. Thank you.